Hey, good morning, everyone. So today we're going to take a quick look at what's known as solving for the point of intersection using substitution. So I'm going to formally introduce a term, but it's essentially what we've been doing every time we solve for the point of intersection um, using the equal values method. So a system of equations just means you have two or more equations that share common variables. So if you look at example 1, we have two equations, they both have x and y. So that makes it a system. So it's nothing complicated, it's just a new name. Substitution is a technique we're going to use where basically we can replace the variable in one equation in special circumstances. And basically that special circumstance is if one of our equations isn't y equals or x equals, but the other one is, then we can use what's known as substitution. So in example 1, notice how this one's already in y equals mx plus b format. And so we might think, oh, let's use the equal values method. But this one is not. It's not y equals, it's not x equals. And so we can't use our equal values method unless we were to rearrange this bottom one. But the nice thing about this is rather than having to rearrange, substitution allows us to avoid that step altogether. So let's take a look at how that works. The first thing I want you to notice is this is y equals. And so, keeping that in mind, let's look at this second equation. I see a y right here. So I'm thinking about these two are connected. So I'm going to think about this second equation as really being 6 times. I'm going to put a blank in there for y. Minus 12x equals 18. So nothing new. The reason I'm looking at this y, once again, is because this equation is y equals. Because it's y equals, I can take this y and I can replace it with what y is equal to, in this case, 4x minus 5. But what I'm going to do is, so I'm replacing y with that 4x minus 5, and I'm throwing it in parentheses, because that means it used to be 6 times y, so now it's going to be 6 times all of this. So now as I start to try and solve this, notice I have a whole bunch of stuff on this side, and so I can use my simplifying process. I can do what is 6 times 4x, and what is 6 times negative 5. 24x minus 30, and then I still have this minus 12x equals 18. All right, and if I look at this side now, I can definitely do some more simplifying. So if it helps you, I'll do a quick rearranging just to put the x's together. This isn't a necessary step, it's just clarifying the simplifying. 24x minus 12x will conveniently be 12x. All right, and now I've simplified this side as much as I can. Let's add 30. Let's add 30. And now I'm left with 12x equals 48. Divide by 12. And now I have x equals 4. So one more time, since y was equal to something in this top equation, and I saw a y in the second equation, all I did was replace the y with this 4x minus 5 in the other equation, and then I simplified and then solved. All right, so we have x equals 4. Technically, to find y, I could use either of these equations, but I'm going to stick to the one that's easier, in this case, this first equation, because it's already y equals something. So I have y equals 4x minus 5, but we just found out that x equals 4. So really it's just 4 times 4 equals 16 minus 5, or y equals 11. So my point of intersection is 4, 11. That's all there is to it. So instead of having to rearrange and then use the equal values method, we can use what's known as substitution. All right, And just to verify, if I take a look at the graph of these two equations, oops, wrong screen. There are my two equations. Sure enough, they cross at 411. And so that's just confirmation that my substitution technique works. All right, so let's take a look at one slightly different situation. This example 2, you'll probably notice that rather than y equals something, we have x equals something. And so what that means is we're going to be looking to replace the x in the other equation. So in other words, we're going to have 5y plus 3 times, once again, I'm going to create my rectangle, because instead of x, since x is equal to negative y minus 9, in parentheses here, I'm going to put negative y minus 9. So instead of the 3 times x that was there, it's now being replaced with 3 times negative y minus 9. Now, if I simplify just like I did before, this 3 has to be distributed into the parentheses. So now I have 5y plus 3 times negative y would be negative 3y, and 3 times negative 9 would be negative 27. This looks kind of ugly, so since it's plus negative 3y, I can always think of it as just 5y minus 3y. So, all right, and that's still all equal to negative 13. I think I can still do some simplifying on this side. I see 5y minus 3y. That would end up being 2y minus 27 equals negative 13. Let's add 27 to both sides. And we end up with 2y equals 14. And then if I divide by 2, get y equals 7. Cool, but I'm asking for the point of intersection. So once again, I could use either equation, but this one's already x equals something. So I'm going to use that one. So this is really negative. So remember, technically in front of this negative y, it's a negative 1. So I'm really thinking of negative 1 times 7. So that's really going to be negative 7 minus 9, or x equals negative 16. So my point of intersection is negative 16, 7. So that's all there is to it. Basically, one more time, if a variable is equal to something, then look for that variable in the next equation and replace it. So x was equal to negative y minus 9, so I'm replacing this x with negative y minus 9, and then I'm just distributing that 3 and solving. So for today's assignment, you'll just be doing a series of these. Let me know if you have questions, but it should be pretty straightforward, and make sure you're checking your answers on the final slide or with the graph, or even better, both.